Hello, welcome to the second lesson into our fourth unit, Unit 4 being on states of matter. In today's lesson, we are looking at the liquid state, phase changes, and the concept of vapor pressure. Our lesson objective is to understand the liquid state using the kinetic model and describe how particles behave during phase changes and at vapor pressure. Just the one learning outcome that we'll be addressing from the curriculum in today's lesson. So, we looked last lesson I should say, at the idea that all matter was made up of small particles that are in constant motion. And that was this theory called kinetic theory, kinetic meaning movement. So the idea that matter is made up of very small particles that are in constant states of motion. So to represent that with a few diagrams, we've got just small particles, very simple spheres, in the gaseous, the liquid, and the solid state. So we looked in depth at the gaseous state, and we said that they have no fixed shape and no fixed volume. Our particles are moving randomly in random directions, having collisions and a high level of kinetic energy. We're going to focus today on the liquid state. Liquid state, they're still moving, they've still got kinetic energy, less kinetic energy than in the gaseous form. However, they're still bound to one another, so they're still sort of held together. They're just free to move over one another and flow. If you think about any liquid, if you think water in a glass, it fixes itself to the shape of that container and it's flowing. The particles are free to move over one another. And then in the next lesson, we'll look at the solid state. In the solid state, we have a very fixed, rigid lattice, and the particles, they're still moving. However, they're vibrating around a fixed point. A very common misconception is that the particles aren't moving in the solid, but that's not true. They're vibrating. It's only at that idea of absolute zero that we looked at in the last lesson, 0 Kelvin, that there's so little energy, there's no energy, that the particles don't even have enough energy to move. Everything has no motion at all. But we'll look at that more in depth in the next lesson. Today we're looking at liquids, and we're also looking at phase changes. So these describe the process of moving between these states by either supplying energy or taking out energy. Now, a lot of these words you use in your everyday life, so I'm sure you're familiar with terms such as melting. That's changing from the solid to the liquid, or the opposite is called freezing, going from the liquid to the solid. The energy needed to do this is called the enthalpy of fusion. That's something we're going to discuss in just a moment. But just recall that enthalpy is essentially just a synonym for energy. So the enthalpy of fusion. Vaporization is when we change from the liquid to the gas form. The opposite being condensation, going from the gas to the liquid form. The energy you need to do this is called the enthalpy of vaporization. And then finally, we have sublimating, which is where we go directly from the solid to the gaseous form, or desublimation, when you go directly from the gaseous to the solid form without ever entering into the liquid phase. So a really useful thing we can do to help us understand how the particles are behaving during the phase changes, so during the melting or the vaporizing or the opposite, and also how they're behaving when you are heating them up, is to graph the energy versus the temperature of a particular substance. This would be applicable for any substance. However, as we go through this, we might want to keep in mind what these effects would look like in water, because that's something that we're very familiar with, all three states of the substance in our everyday lives. We're very familiar with ice cubes when it's solid, regular just water, and then steam when it's in the gaseous form. So bear in mind that these phase change diagrams, this would be applicable for any substance as it goes between the states, but we're just going to sort of relate it back to how that would look like in water. So if we start off with a cube of ice, we have an ice cube in the solid form. It's got a very fixed three-dimensional lattice, fixed volume, fixed shape. As we increase the energy supplied, so we might want to picture if we were heating this ice cube up, if we were putting it over a Bunsen burner and then recording the temperature changes as we supply energy into that system. So as energy is increased, the particles will vibrate more vigorously, they gain more kinetic energy, and as a consequence, the temperature would rise, because essentially that's all temperature is, just a measurement of the particles' kinetic energy. As they vibrate more, they're still vibrating around a fixed point. They've still got a fixed volume and a fixed shape. However, the temperature is increasing because they're moving faster. But then we'll reach this point where the temperature will flatline, and this is the melting point. Now you see something very interesting here. Whilst it's melting, the temperature doesn't rise any further. The temperature stays the same until all of the substance has completely melted, and only once it's completely in the liquid form will it continue to rise in temperature. So we're still increasing energy during this section. You can see we're going up in our energy down on our x-axis. However, the temperature doesn't increase. And this is because the heat energy is now being used to break the bonds between the particles as opposed to increasing the kinetic energy. So they're at the point where the particles aren't going to move any quicker. The energy is now going to be used to disrupt the bonds, the attraction between the particles, as opposed to increasing the kinetic energy. And it's only once those bonds are broken, it's in the next phase, that the kinetic energy will begin to increase again, like so. Oh yeah, actually, I'll talk about that in a second. And then we'll get to the liquid phase here. So the energy that we need to melt it, the energy that will be seen in this point where the graph doesn't rise in temperature any further, this is showing us the enthalpy of fusion. The energy needed here will be the enthalpy of fusion. So this is telling us how much energy we need to supply in order to go from the solid to the liquid state. Now these will be unique for given substances. The value for the energy needed for the enthalpy of fusion, however, it'll always be shown by this section on the graph. Once we've melted, we are now in the liquid form, where the particles are still bound to one another, however, they're free to move and flow over one another. This says, as the energy is increased, particles move faster, gain more kinetic energy, the temperature is increased. So this sort of mirrors what we saw in this section when it was in the solid form. The particles with the most energy are the first to escape from the forces holding them together, i.e. the particles at the surface. So some evaporation will occur beneath the boiling point. This is something we're going to talk at in depth in the next part of this lesson. However, you might notice if you leave a glass of water out, even though it's not at the water's boiling point of 100 degrees Celsius, you can still get some sort of evaporation. And that's essentially because when we talk about temperature, temperature is just an average reading of the whole system, right? So there are particles that might have their specific kinetic energy higher than what the net or the average kinetic energy of the system is, and there might be some that are lower. So specifically at the surface, the particles that will be at the surface of the container are going to have a higher kinetic energy, and some might even reach that boiling point, whilst the average, so the sort of combined or a sample of the kinetic energy of the system is still below the boiling point. But like I say, we're going to talk about that on the next section. So then you might predict that we will get to the boiling point where we see a similar thing to the melting point. We still add energy, however, we stop increasing the temperature because of the same reason. The heat energy is now breaking the bonds between the particles as opposed to increasing their kinetic energy. The forces will eventually weaken enough for all particles to become completely free from each other, and then it will be in the gaseous state. So similar to this section being the enthalpy of fusion, so the energy needed in order to have a phase change between the solid and the liquid, you might predict that this is going to be the enthalpy of vaporization, this energy value here. So this is the energy needed to go from the liquid to the gaseous form. Again, that's going to be different for different types of substances. However, the trend, this general trend will be the same in all cases. Then finally, once we have all reached the boiling point and everything is in the gaseous form, we will then see the energy increase again as we supply energy into the system because the particles will move faster, gain more kinetic energy, and the temperature will continue to rise like so. So that gives you a good overview. Solid phase, melting point where we can get that energy value to be the enthalpy of fusion. Then the temperature will increase in the liquid state. Where we reach the boiling point, that energy will be the enthalpy of vaporization needed to go from the liquid to the gaseous phase. Then we enter the gaseous phase and the temperature will increase as we supply more energy. If we think of our case of water, we've got the ice down here. We warm up the ice cube until we get to the melting point of water. So if this was for water, this would read at 0 degrees Celsius because that's when water freezes, when it's the freezing point of water. This would be the enthalpy of fusion, so how much energy we need to melt it. Once it's all melted, the temperature would start to increase again as we got our liquid water. And then we'll reach the boiling point. So this would read 100 degrees Celsius for the boiling point of water. This would be the energy needed to boil it all. And then once we enter the gaseous stage, we see all the steam coming up, all the water vapor. Excellent. Let's go to the second and last part of the lesson today, just a short one really. Vapor pressure. Temperature isn't necessarily distributed evenly. When we take a measurement, we are getting an average of the kinetic energy of particles in the system. So that's what I was discussing about before, the idea that if you put a thermometer into a cup of water, you're really only getting a reading of the average of the particles that are colliding with that thermometer to show you the average kinetic energy, thus the temperature. So it's really only an average of a sample of the system that you get the temperature of when you measure it in certain ways, such as with a thermometer. We also said phase changes are reversible, so you can melt something and then you can freeze it, you can go the opposite way, you can vaporize something and then you can condense it. But relating to this point here, in the liquid form, particles can evaporate below their boiling point as particles at the surface can have a higher kinetic energy, i.e. temperature, than the average temperature of the system. So that's what we were saying before, where you can leave a liquid out, and even if it's not at its boiling point, it can still slowly evaporate because the ones at the surface can have a higher kinetic energy than the ones that are lower down, that are deeper in the sample. So bearing all that in mind, let's consider a closed system. So we've got a liquid in a container that has a lid. Some of the surface particles will become water vapor. And I'm going to draw a picture. All right, so I've got a closed container like so. In my container, I have some sort of liquid. That's good enough for my container. My liquid, it has the shape of the container. The particles are still sort of bound to one another. I should have done these a little bit bigger. But they're free to flow over one another and move about. So what can happen is that even though this sample might be below this particular liquid's boiling point, we can still have some of the particles that are on the surface enter the gaseous phase. They can vaporize. So I might have one on the top that can have enough kinetic energy that it enters the gas. Then, what does it say? As more particles escape, the molecules in the vapor become more tightly packed. Eventually, some particles with lower kinetic energy cannot overcome the attractive force of neighboring particles and will condense again. What do I mean by that? So, over time, I'm not going to bother with my ruler. I'm just going to try to draw a square as neat as I can. I got the same liquid. If I fill in all my dots, I definitely should have done these dots bigger. These were meant to be the same size. So as time goes on, we get more particles enter into the gaseous phase. So I might have 3, 1, 2, 3. And then I got my original one that was in the gaseous phase, that fella just there. But it says, more particles escape, the molecules in the vapor become more tightly packed. So these particles here, as more become in the vapor of the closed system, the ones become more tightly packed. And eventually, it'll cause some of these particles to have less kinetic energy and go back down into the liquid phase. So do the reverse. It'll condense like that. From there, eventually what will happen is an equilibrium will be set up. An equilibrium means a balance. Eventually an equilibrium will be reached as particles will evaporate and condense at the same rate. So, over time in my closed system, I will eventually get an equilibrium where the particles are moving between the gaseous phase and the liquid phase at the same rate. So you won't see any net overall change. However, that doesn't mean that nothing's not happening. It just means that they're going in and coming out at the same rate as each other. So equilibrium is a word that we're going to be hearing a lot of this in this course, and it essentially just means a balance, balance where the rate has been balanced. All right, and we can represent that with an equation. So we would have the water molecules. If this is water, there could be any liquid. In my case, I'm just doing it with water. Water molecules in the liquid is in an equilibrium. So this is an equilibrium arrow. So this is showing that we can go this way, but we can also go this way. And in this case, it's doing this at the same rate. It's an equilibrium with the water molecules in the vapor. Water molecules in the vapor. So this means that the rate of the change is equivalent, an equivalent rate. So what the vapor pressure is it is the pressure that is observed whilst this equilibrium is achieved in a closed system. So if we think back to the previous lesson, we discussed the idea of pressure being the force exerted on a container by gas particles as they collide with it. So if we've got gas particles in the in this equilibrium here, these are still colliding with the container. So the vapor pressure will be the pressure that is observed once this equilibrium is reached. Once the rate of the water molecules going to the liquid is the same as the rate of the water molecules going to the gas. The temperature at which vapor pressure equals the atmospheric pressure, that will be the boiling point of the liquid. Excellent, and with that we finish the lesson, just a short one for the liquid state. What have we done? We have described using a kinetic molecular model the liquid state, melting vaporization, and vapor pressure. Some tasks that you can do if you want to consolidate your understanding of what we've covered. As always, you can pause, work through the columns one at a time, starting from the bottom, going up. Lovely. That is it for today. I will see you on the next one when we'll finish off this unit by looking at the solid state. Thank you very much. Goodbye.